the last part of today's lecture, we're going to combine the pieces that we've learned about so far to go through the classic transformer model. So let's talk about how we can do sequence to sequence with self-attention. There are a number of model designs that use successive self-attention and position-wise nonlinearity to process sequences. And these are generally referred to as transformers because they transform one sequence into another at each layer using these self-attention mechanisms. So for the classic transformer, you can check out this paper by Vaswani et al. Called Attention is All You Need. Now there are other ways that people have used transformers besides the one described in this paper, including for building very powerful language models, which we'll actually discuss next time. But the classic transformer, the one described by Vaswani et al., is actually a sequence-to-sequence model. A number of well-known follow-up works also use transformers for language modeling, and that will be discussed later. Okay, so on this slide, what I'm going to do is I'm going to sketch out the classic transformer model with a side-by-side comparison to a sequence-to-sequence RNN model, like the ones we've seen before. So a sequence-to-sequence RNN model has an RNN encoder and then an RNN decoder. And these can in general have multiple layers. Here I have it drawn with just a single layer. To make this into a transformer, we will basically replace the encoder and the decoder with successive self-attention layers alternating with position-wise nonlinear transformations. So the encoder is going to get a sequence of x's with corresponding positional encodings, P1, P2, and P3. At every position, we will encode these. Then we will pass it into a self-attention layer. So at every position, we'll compute some ht1, because it's the first layer, and those will produce keys, values, and queries, and they'll actually produce 8 keys, values, and queries for multi-headed attention. And then we'll do multi-headed self-attention without masking at this point. And then we will take the output of this multi-headed attention and pass it into a position-wise nonlinear network. Basically, at every position, we will apply some nonlinear function to that attention vector to get the hidden state at the next layer. This is going to be h2. And this is repeated n times. So we have n of these blocks: self-attention, position-wise nonlinearity, self-attention, position-wise nonlinearity. So that's the encoder. So the encoder is going to have n of these layers. Then in the decoder, we're also going to have a position-wise embedding of the output steps and their corresponding positional encodings. And we're going to be using masked attention here. So even though it kind of looks like we're inputting all the time steps, in reality, y1 will actually come from the output at time step 0. So that's okay. We're going to have masked self-attention now, which means that earlier time steps don't get to look into later ones, only into earlier ones. Then we'll have a position-wise nonlinear network. And then we're actually going to have something called cross-attention, which is going to use all of those hidden vectors produced by the encoder. Cross-attention is very much like the classic attention that we described in the previous lecture. So instead of self-attention, which looks at other time steps in that same sequence, cross-attention is going to look at the time steps in the encoder. So it's going to actually reference the corresponding layer of the encoder. So layer 1 of the decoder references layer 1 in the encoder. Layer 2 cross-attention in the decoder references layer 2 in the encoder. And then we'll discuss in detail how this works shortly. And then after cross-attention, we have another position-wise nonlinear network. So every decoder layer actually has 2 attentional steps. It has a masked self-attention, nonlinear function, cross-attention, another nonlinear function, and then that goes into the next block. And these blocks are also repeated n times. So the decoder blocks have twice as much stuff going on as the encoder blocks. And then at the very end, after n blocks like this, then we apply a softmax at every position and read out the output. So when we're actually decoding with the decoder, we still do it one step at a time because we're using masked attention. And then we, just like in the RNN, we feed in y1 hat as the input y1 at the next point in time. And we're able to do this because we use masked attention. Okay, so let's talk about this cross-attention mechanism. It's a little subtle. So we're going to use ht superscript L to denote the hidden states at layer L in the encoder, and SL superscript L to denote the states in the decoder, just like we did with the RNN. Only now these states are produced by the position-wise nonlinear network instead of by a recurrent network. So cross-attention is much like the standard attention from the previous lecture. We have a query which we compute by applying some matrix WLQ to the state. So the state here is the output of the position-wise nonlinear network at the decoder layer L, step L. These are two different L's, script L and normal L. The key is constructed in the encoder, so KTL is obtained by applying some linear transformation WKL to the hidden state HTL. And the value, VTL, is obtained by applying a linear function, WVL, sorry, there's a little typo, it should be WVL, times HTL. So HTL here is the output of the position-wise nonlinear network at encoder layer L at step T. Okay? So far this is exactly the same as a standard attention that we saw before with seek-to-seek models. And then we compute an attention score between every T and L. And here now the T's come from the encoder, the L's come from the decoder. We apply the softmax, and then we compute our cross-attention CL as just the linear combination of the VTLs weighted by alpha LTs. So this is our cross-attention output. Okay, this is exactly the same as the regular seek-to-seek attention that we had before. Now in reality, cross-attention is also multi-headed. And actually, in the classic transformer model, it has the same number of heads as the self-attention. So we're going to have 8 heads for cross-attention. Okay, so that's cross-attention. Now there's one more little detail that we need to discuss before we can present the full real transformer model. And it's a little bit different from all the rest, but it's important to understand the full implementation. And that's something called layer normalization. Okay, this has nothing really to do specifically with attention models, but it turns out to be important for the transformer because it's difficult to use regular batch norm with transformers. So the main idea here is that batch normalization is very helpful, but it's hard to use it with sequence models for a few reasons. Sequences are different in length, which makes normalizing across the batch kind of hard, and sequences can be very long, so we sometimes have very small batches, making batch norm less effective. So a simple solution that we can use is to replace batch normalization with something called layer normalization. Layer normalization is like batch norm, but it's across different activations in a layer instead of different samples in a batch. Generally, at least from my experience, layer normalization is a little bit worse than batch normalization for the types of models where batch norm can be used effectively, like big confidence. But in some cases, batch norm is just very difficult to use, in which case layer normalization is better than nothing. Okay, so I'll describe layer normalization in contrast to batch norm. So first, let me summarize the standard batch norm that we already learned about. In standard batch norm, at every layer, you have a bunch of activation vectors, one from every input. So you have capital B different images in a batch, or different, whatever, inputs. And for each one, at some layer, you compute a different activation vector. So each of these A1, A2, A3 through AB is a d-dimensional vector, where d is the dimensionality of that layer. And then batch norm computes a mean and a standard deviation over all of the points in that batch, over all of the inputs in that batch. So mu and sigma here are d-dimensional vectors. So these are all per element operations, and if your activations have d dimensions, mu and sigma also have d dimensions. And then when you transform them with batch norm, everything is per element. So for every element of every sample's activation AI, you subtract the corresponding element of mu, divide by the corresponding element of sigma, multiply by the corresponding element of gamma, which is the learned scale, and add the corresponding element of beta. So the subscript I here indexes different points in the batch, different data points. And all operations are per dimension. Layer norm is a little different. So layer norm is going to be a more traditional layer. It doesn't use any information across the batch, it just uses information within a single data point. And instead of computing the mean over different vectors in the batch, it actually computes a single number, a single one-dimensional quantity, by averaging together the activations for every dimension. So here, the subscript j actually indexes different dimensions of A. And there's a small typo, there should be the sum of j equals 1 to d, not I. Okay, and you divide it by d now. So it looks like the same equation, but it's actually doing something very different. It averages together the activations over that vector, and it's one-dimensional. And the standard deviation is calculated the same way. It's a sum. Again, there's a typo j equals 1 to d of aj minus mu. Mu here is a scalar value. Sigma is a scalar value. And then just like before, you transform the activation, subtract mu, divide by sigma, and then element-wise multiply by a vector gamma, and element-wise add a vector beta. So gamma and beta are still per element, but mu and sigma now are scalars. Right. So now this doesn't require any sharing of information across the batch, which means that it's quite straightforward to use this with sequences. All right, so now we actually have all the pieces that we need to put all of this together and actually derive the full transformer model. So the diagram that you see on this slide, which we'll walk through in a lot of detail, is actually from the paper that introduced the transformer called Attention is All You Need. And what this paper proposed is to use successive self-attention and position-wise nonlinear functions to actually implement a sequence-to-sequence model, which they apply to machine translation. So we start off by taking our input sequence, separately embedding every token in that input sequence, and adding the corresponding positional encoding to that embedding. And then we have our first multi-headed self-attention layer. So the input we'll say is h bar t l minus 1. You'll see shortly why I'm calling this h bar. So h bar t0 is just the input embedding plus the positional encoding. H bar t1 is going to be the output of the first block. So we'll see what that means shortly. And the output of the self-attention layer we're going to call a subscript t superscript l. So it's just a self-attention layer with multiple heads. They use 8 heads, and they use a dimensionality of 512 for h and a. So you concatenate the attention from all the heads to get ATL at every position. And then you have this thing called add a norm. And what this is you can basically think of it as a residual connection followed by a layer norm. So a bar TL is going to be obtained by applying layer norm to h bar TL minus 1 plus ATL. So you take the input to the self-attention, and then you add the output of the self-attention, and then you apply layer norm to that whole thing. So this is essentially a residual connection with layer norm. So if you think of your function as self-attention, then ATL is basically f of HTL minus 1, and then you do HTL minus 1 plus f of HTL minus 1, which is just a residual connection. And then you apply a layer norm to that whole thing. Now the reason they do this is because they essentially want every layer here to be a modification. And they want to obtain that benefit of well-behaved gradients that you get from residual connections. Then you have a position-wise nonlinear function. And the particular position-wise nonlinear function that they use consists of a linear layer, then a ReLU, then another linear layer. So they do W1L times A bar TL plus B1L. So that's the first linear layer. Then they apply a ReLU to that. And then they multiply it by W2L and add another bias, B2L. So it's linear, ReLU, linear. And that gives them HTL. And HTL you can think of as the pre-layer norm hidden state. So this is basically just a two-layer neural net at each position. And then they have another add a norm. So it's again a residual connection. So you take AT bar L, which is just the input to this position-wise nonlinearity, and then you add HTL, which is the output of the position-wise nonlinearity, and then you apply a layer norm to that whole thing. And that is now passed to the next layer, to the next block, L plus 1. So they have n of these blocks. So each block is multi-headed self-attention, add a norm, position-wise nonlinearity, add a norm, pass it to the next block. Multi-headed self-attention, add a norm, position-wise nonlinearity, add a norm, pass it to the next block. And they use, I believe, six of these blocks. Each of them has a dimensionality of 512. So all the H's and all the A's have 512 entries at every position in the sequence. And I believe they use 8 heads for the self-attention. Okay, so that's the encoder. Now, once you've run the encoder all the way forward, you will have computed 6 of these blocks, and at every block, you will have a different H bar TL. And it's these H bar TLs that are actually going to be passed to the decoder. So in order to pass it to the decoder, they actually compute multi-head attention keys and values. So KT1L through KTML and VT1L through VTML for m different heads. I believe the number of heads is 8. And they do this at every one of those 6 layers. So these Ks and Vs are really the thing that the decoder is going to use, and they come from HT bar L. Okay, so that's the encoder. Now, the product of the encoder, the result of running the encoder, is these keys and values. That's what we want to get out of them. Now let's talk about the decoder. The decoder has the same kind of positional encoding business. And then each block of the decoder, for every encoder block, there's a corresponding decoder block. So there's 6 of these blocks. But the blocks are a little more complex. So it has a multi-headed self-attention, just like the encoder, only now the multi-headed self-attention is masked, so that at every time step it only looks at past time steps for the decoder. And that's because the decoder is going to be used to actually generate a sequence. Then it has the same kind of add-on norm, so a residual connection with a layer norm. And then it has a second attention, which is this cross-attention. So the cross-attention produces queries based on the output of the self-attention, and those queries are used to look up the keys and values from the encoder. And then again, it has a add-on norm. So this is actually very important because the add-on norm will actually add together the result of cross-attention and self-attention so that you have both of those pieces of information. Then you have a position-wise nonlinear function, which uses the same architecture but different weights as the encoder. And then you have another add-on norm, so residual connection with layer norm, and then you pass that into the next block. And then at the end of the last block, the 6th block, there's a linear layer at every position, followed by a softmax, which actually outputs a probability distribution over the token at that position. So the decoder decodes one position at a time with masked attention. So you encode the entire input sequence, then you start decoding, and you first start with the first token, which is just like a start or something. Now self-attention there is not doing anything interesting, but cross-attention is. And then you have all these alternating layers. Then you can produce the output at the first position. Then you feed that in as input into the second position, and then the whole process repeats. So the decoding is done one position at a time, just like in an RNN, only using these attentional mechanisms. Okay, so that's the summary of the full transformer model. It is a sequence-to-sequence model with alternating self-attention and feed-forward networks with add-on norm between them for the encoder, and then self-attention, cross-attention, feed-forward for the decoder. All right, so why did we bother learning about transformers? What's so great about them? Well, they do have some pros and cons. Some of the downsides of transformers are that attention computation is technically O of n squared, which is maybe a little bit of a problem because for RNNs everything is O of n, whereas now we suddenly have O of n squared. But this is not quite as big of a problem as it seems, because even though attention calculations are O of n squared, most of the computation time is actually not spent performing those dot products. It's actually spent on all the other parts of the network. So it's O of n squared, but with a relatively small multiplier, and then it's O of n with a really big multiplier. So in practice, in terms of computational cost, oftentimes transformers are actually a lot cheaper than RNNs, because even though they're quadratic, it's quadratic with a very small coefficient by comparison. Or put another way, there's a quadratic part with a small coefficient, and there's also a linear part with a similar or slightly smaller coefficient. They're also somewhat more complex to implement and involve a variety of seemingly weird decisions like positional encodings, which can make them a little tricky to work with. And it can take a fair bit of hyperparameter tuning to get transformers to train well. They do, however, have a number of really important benefits. First, they have much better long-range connections. So essentially, every position in the output is connected to every other output position and every other input position with a jump of length 1. They're much easier to parallelize. So computationally, implementing a transformer on parallelized hardware like GPUs makes them run much, much faster. For RNNs, every step has to be processed one at a time. For a transformer, the encoder is entirely parallel. The decoder requires that one step at a time calculation, but it's still not too bad. And in practice, you can make transformers quite a bit deeper than stacked RNNs. So for stacked RNNs, maybe like 3 layers is about kind of the max that people use. For transformers, six of those blocks is pretty typical, and each block actually has multiple layers. In practice, the benefits of transformers seem to vastly outweigh the downsides, and transformers work much better than RNNs and LSTMs in many actual practical sequence-to-sequence processing cases. And arguably, the transformer architecture is one of the most important sequence modeling improvements of the past decade, so it led to a huge gain in the performance of neural network models in NLP. Okay, so what are some of the results for transformers? Well, these are results on translation, English to German and English to French, in the original Vaswani et al. Attention is all you need paper. Okay, so let me explain how to parse this table. At the bottom, you have the 2 transformer models, a smaller model and a larger model. And then all the other methods are various convolutional and recurrent models for processing sequences with all sorts of other tricks like ensembling and so on. The first 2 columns show what is called a blue score, which is a way to measure translation performance. The first column is English to German, the second column is English to French. The third and fourth columns show the number of floating point operations that are needed to train these models. And for the transformer, the numbers are the same for English to German and English to French. And the thing to pay attention to is the exponent. So it's something times 10 to the something, and it's that exponent that matters. And you can see that among all the models listed here, the transformers are actually the cheapest in terms of computational cost. So their training is actually faster, despite the fact that they end up performing better. So in practice, the fact that they're faster means that we can use larger models for the same cost. And a larger model typically yields better performance. In fact, transformers are better able to scale up so they can be larger for 2 reasons. They're more scalable and they train faster. And of course, they end up getting great translation results, better than all the previous models, in the case of English to German by quite a large margin. And it's also worth noting that some of the models they're comparing to are like ensemble models, whereas they're not even bothering to ensemble the transformer. Here's a very different application. This is text summarization. So long document comes in, shorter document comes out. And the measure of performance here is perplexity, and they're comparing to a sequence-to-sequence attentional model, which was kind of the previous state-of-the-art for this. Perplexity, you can think of it basically as roughly 1 over likelihood, so lower is better, and it basically corresponds to how well the model captures the probability distribution over sequences, so basically the probability that it assigns to true sequences, except it's 1 over likelihood, so lower numbers are better. And you can see that there are very large gains in terms of perplexity for all the transformer models as compared to the sequence-to-sequence RNN model with attention. So transformers end up working a lot better in these kind of sequence-to-sequence style applications. We'll also learn about the power of transformers as language models next time. So while transformers have had a big impact on sequence-to-sequence modeling, they've had an even bigger impact on language modeling as a way to do representation learning. So we'll discuss that next week.